And hello, algebra students. It's our last section for now for chapter 1. We're going to move chapter 8 or section 8 to a different part. So, section 1-7, functions. Functions is a technical term, and a function is, well, it's in there somewhere, the relationship between the input and the output, between the x and the y, or between the dependent and the independent variables. So our objective for this section is to determine if a relation is a function and then find values of functions. That implies to me substitution, order of operations. So it's just a relationship between the input and the output. They're the x and the y. Here's the thing, here's the most important rule about a function. I feel like this is a highlighting worthy. Most important thing about a function is that each element of the domain is paired with exactly one, not more than one, exactly one element of the range. If you need to wrap your brain around that in a different way, let's say you can't repeat x values because an x value can't have more than one y value. And let's just note that you can repeat y values. So being allowed to repeat y values but not x means that all of your x values or your domain has exactly one pair in the range, not more than one. So you can't have an ordered pair 1, 2 and 1, 3 because then it has more than one pair in the range. So we're going to look at our 4 ways to show relations. We're going to look at mappings, tables, graphs, and ordered pairs and determine if they are a function. So function is a set of ordered pairs, just like relations, only the rule is you can only have the domain paired with one element of the range. So when I look at number 1, notice I've got a mapping here. I've got -4 pairing up with 9, -1 pairing up with -6, 1 pairing up with -6, and 3 pairing up with 7. If our directions say to determine whether each relation is a function, it's a yes or no question, right? If these are my x values and these are my y values, is each value of my domain have only one value in the range? Or do we have any repeats in the x values? So yes, this is a function. And I'm just going to put, for my explain reason, I'm going to put there are no repeats in the x. Are there repeats in the y? Or in the dependent variable? There are, right? -6 is the y value for 2 different x's, but it's okay to have repeats in the y's. How about our table for number 2? Is this a function? This is not a function. Why is it not a function? If I said this is not, tell me why. You are going to tell me that we have 2 2's. So we've got an ordered pair 2, 5, and we've got an ordered pair 2, 4. We cannot have repeats in the x. So we've got, so this is not a function. And then we've got a bunch more. Before we get to number 6, we can look at that as graphs. Are you getting the feeling for this? Number 4, we actually need to mention really quickly. Just a little hint to you. You probably, hopefully remember slope-intercept form. Whenever you can write an equation in slope-intercept form, yes, this is a function. Because if we graphed that, we would just have ourselves a line like this, and we're all good to go. So yes, this is a function because we can write it in y = mx plus b form. And it's in y = mx plus b form because the y is all by itself on the one side of the equation, and then we've got ourselves a 5x minus 2. So we're looking for repeats in the x. Number 6, we could look for repeats in the x, right? So if I name these points, this is -3, -1. This one is -3, -3. This one is -3, -5. This one is 0, 3. Lots of 3's in here. This one is 2, 3. And this one is 4, 3. Do we have repeats in the x's? We do over here, right? So this is not a function. Repeats x values. However, when we've got a graph, we could look at this a little bit differently. So we can look at the vertical line test. A vertical line test says if you draw a vertical line on a graph, it will only touch the graph in one point. So vertical is which direction? So I'm going to draw myself a vertical line, nice and straight. So if I roll this vertical line over, notice how it's only touching my blue line at one point at any given time. It never touches more than once. So if that happens, then yes, this is a function. And in this case, I would say it passes the vertical line test. How about this one over here? Notice, is it only touching the blue line at one time or one point at a time? Look at right here, we've got a touching here and touching here. So this is not a function. So it's another way to check that. We could find ordered pairs for those points and see that we've got repeats in the x's, or we can cheat a little bit with this vertical line test and it tells us if the x's get repeated. So it's really the same thing, it's just a visual way to see that repeat of the x's. So doesn't pass vertical line test. Have you gotten used to my handwriting yet? Sometimes I get a little sloppy. This one's an interesting one because over here on the left side of the graph, it definitely passes the vertical line test. Over here on the right-hand side of the graph, it definitely passes the vertical line test. But what about right in the middle on the y-axis? What do you notice about the circles? The one up on the top, right, is an open circle. Can you kind of see that it's hollow? The one on the bottom is closed. So I'm going to make a note. This is an open circle, which means that it includes all the points except exactly that value. This one is a closed circle, so it includes everything, which this means that this is a function because it technically doesn't touch my pink vertical line more than once because this one is closed and touches the pink line. This one is open, so it doesn't technically touch that. So it does pass the vertical line test. So let's talk about function notation then. So if it is a function, we can just name these in a fancy way. So we're going to name functions in a hoity-toity manner. Notice on the side box I've got an equation y equals 3x minus 8. That's how we say an equation, right? It would be a function because we can put in mx plus b form. It's already there. If we're going to call it a function, we've got this new notation. And maybe you've seen that before, but all that is a fancy way to say y equals. There's really no difference. Everything else is the same. So you read it as f of x. So for that function, I would say f of x is equal to 3x minus 8. It's the same as saying y equals. Even sometimes on a graph, when we get into these functions, we'll have the x-axis, and then they'll get super fancy and call that the f of x-axis instead of saying the y-axis. It is the same thing. Do not be intimidating. We're just replacing the y equals with f of x equals. And then we can start finding values. So in this function f of x equals 3x minus 8, what if I said find the value if x equals 2? So we can find the value of the function of x when x equals 2. So that tells us wherever we see an x, we put a 2, substitution, and we go ahead and do the evaluation. And you might already know the answer is -2. So values of function is just a substitution. You substitute your value for x and simplify. So down here in practice, number 12, it says to find each value. If f of x is equal to 2x plus 5, find each value. So A, I say find f of -2. Well, we're just going to do that. We're just going to put a -2 in. Since this x is inside the parentheses, we're going to replace it with the -2. So I'm going to do f of -2 equals 2 times instead of the x. Substitute that. Do the math. Multiply before I add, so -4 plus 5. So f of -2 is equal to 1. If I want to do f of 1 plus 4, notice I'm going to find the value of f of 1, and then I'm going to add 4 to the answer. That plus 4 is not inside those parentheses. So I'm going to do f of 1 is equal to 2 times 1 plus 5. Don't forget the rest of that. I'm going to highlight it so I don't forget. So 2 times 1 to multiply, I get a 2 plus 5. So f of 1 is equal to 7. So f of 1 plus 4 is equal to 7 plus 4, right? Or 11. I like example C the best. Find f of x plus 3. Notice how x plus 3 is all in the parentheses. So that means wherever I see an x, I'm going to substitute in an x plus 3. It's going to look weird. So f of x plus 3 is equal to 2 times, instead of putting an x, I'm going to put the other stuff. So I'm going to put this x plus 3 inside there. Just like that's exactly what we did with the f of 1, we put a 1 in for the x. This one, though, it's just a matter of simplifying instead of evaluating because we can't get a definite answer because we still have an x in there. So I'm going to do the distributive property. 2 times x is 2x. 2 times 3 is 6. That plus 5 is still sitting at the end. I see one pair of like terms. So f of x plus 3. Can the 2x combine with anything? 6 plus 5. And my final answer is 2x plus 11. I can't simplify and get a 1 or an 11 because, like I did on A and B, because I have a variable still in that problem. So in these guys, notice the equation's a little trickier, but that's all right. You can do this math. It says h of z this time. So notice z is the variable in the parentheses, and z is also the variable in the problem, z squared plus 3z minus 4. I'm just saying the function is called h instead of f. Just a weird way to do it. Sometimes if you have more than one function, we'll call one f, one g, one h, whatever. So it's still a function. So the function h in terms of the variable z is z squared plus 3z minus 4. So if I want to find h of -4, I'm going to do exactly the same thing. Wherever I see a z, I'm going to replace it with a -4. So h of -4 is equal to -4 squared plus 3 times -4 minus 4. There's a lot of 4's in here. But notice I did substitution with those z's in the problem, and I put -4 in there and -4 in there. So now I'm going to just do the math. So -4 squared. Squaring is always a positive experience, right? -4 times -4 is positive 16. If you put it in your calculator and get a -16, you need to put parentheses around the -4 before you square it. 3 times -4 is a -12 or -12 minus 4. You could say that that was plus a -12 if you wanted to. It's the same thing, remember, subtracting and adding a negative. So when I do this math, I get a very interesting answer. I think, if I'm doing my math right, h of -4 comes out to a 0. We'll talk more about letter B, but this is evaluating a function. Really quickly, we're not going to hit these super hard, but I just want to mention them. A discrete function is when you have a graph and it's a straight line. A continuous function is when you have a graph and it's either a line or smooth. It doesn't jump around. And nonlinear, they are not connected and not a straight line. You could connect them, but let's change that. Not straight. Just a little bit of terminology. Don't get too stressed about memorizing those, as long as you kind of have an idea that it's just about what the graphs look like. So, lesson summary. If I give you a set of ordered pairs, how can you tell if they're a function or not? Like, here's 5 ordered pairs. Tell me, is it a function or is it not a function? And explain. Just like the first examples. And make a mapping for that relation. Remember, the mapping is where you do your 2 bubbles. And you've got arrows going from one. So go ahead and make that mapping from a previous section, but also tell me, is it a function? And please explain. As I cough my way out, have a great day. That's the end of 1-7. We'll do some reviewing so you're ready for the Chapter 1 test. Bring your questions to class. We'll see you next time. Have a good one.